Thank you for your attendance to our talk. The title of the talk is An Optimal Separation of Randomized and Quantum Query Complexity. This is a joint work with Alexander Shostop and Andrei Starchenko. A central problem of quantum computing is how much faster can quantum computers be than classical computers? Most of the research focuses on the query model, which is tractable enough to allow unconditional lower bounds, yet rich enough to capture most of the known quantum algorithms. In the classical setting, a deterministic query algorithm is a decision tree. For example, in this picture, we would first query the variable x1. Depending on the value of x1, we either query x2 or x3. And we repeat this procedure till we reach a leaf, whose label should be the value of the function. Throughout this talk, we'll use the -1,1 representation to encode the input bit of a function. A randomized query algorithm is simply a distribution on decision trees. We say that the randomized decision tree computes f with area epsilon if for any input x, the probability that the algorithm outputs a wrong value is at most epsilon. Sometimes the function is not defined on the entire Boolean cube. Then the correctness criterion only applies to the inputs with defined outputs, and we call such function partial function. On the other hand, for functions defined on the entire Boolean cube, we call them total functions. The randomized query complexity of f with respect to the error parameter epsilon is the minimum depth of a randomized decision tree for f with error epsilon. So that was a classical randomized setting. Now let's review quantum query algorithm. In a quantum algorithm, we can put queries in superposition. As a result, in a single query, we will be able to access all xi, but these values are stored in the amplitudes of the quantum states. It is not immediately how to extract the information we need. The query model plays an important role in quantum computing. It captures nearly all quantum breakthroughs. Here I list a few well-known algorithms, including Shor's factoring algorithm and Grover's search algorithm. A natural and fundamental question to ask is, how much more efficient can a quantum query algorithm be than a classical query algorithm? Simon was the first to exhibit an exponential speed up of the quantum algorithm over the randomized algorithm. In particular, he showed that there is a function who has a quantum algorithm using only log n queries, but a randomized algorithm requires at least square root of n queries. Simon's work raises a natural follow-up question. What is the largest possible separation between randomized and quantum query complexity? For example, can they exhibit a linear versus constant separation? This question was first explicitly asked by Berman et al., and then by Aronson and Albinus again. Towards resolving this question, Aronson and Albinus introduced the Rorrelation problem. They showed that there is a quantum algorithm using a single query that solves the Rorrelation problem. However, in a randomized query algorithm would require at least square root of n queries. In addition, they also proved the following simulation result. They showed that for any quantum algorithm with k over 2 queries for a constant k, then there is a randomized algorithm that simulates this quantum algorithm using n to the 1 minus 1 over k queries. So this simulation result rules out the linear versus constant separation that one might hope. In recent years, Paul generalized the Fourier problem, and he refers to the generalization as the Rorrelation problem. The Rorrelation problem is a family of problems defined with respect to a parameter k. He showed that for the Rorrelation problem, there is a quantum algorithm using k over 2 queries, but any randomized algorithm will require at least n to the 2k minus 2 divided by 3k minus 1 queries. In our work, we give a tight analysis of the Rorrelation problem. In particular, we prove that the randomized query complexity of the Rorrelation problem is in fact n to the 1 minus 1 over k. In view of Randomized and unbiased simulation result, this is optimal. This separation is the best that one can get. In more detail, what we proved is the following. For any positive integer k, no larger than log n over 3, then there is a function, a partial function, such that its quantum query complexity with respect to this error parameter is k over 2. But the randomized query complexity with respect to this error parameter is n to the 1 minus 1 over k divided by log n to the 2 minus 1 over k. For a constant k, these error parameters are all bounded away from the half. Of course, one can apply the standard error reduction to get complexity measures with respect to the more familiar error parameter of a third. In that case, the quantum query complexity is exponential in k, and the randomized query complexity is still n to the 1 minus 1 over k divided by polylog n. We can also choose different k to exhibit different kinds of separations. For example, we can take k to be a large constant. Then we get the constant versus n to 1 minus epsilon separation of quantum and randomized query complexity for an arbitrarily small positive constant epsilon. We can also take k to be a slow-growing function. Then we get a slow-growing function versus n to the 1 minus little o1 separation of the quantum and the randomized query complexity. All these results are for partial functions. For total functions, it is well known that the quantum and randomized query complexity are polynomially related. Prior to our work, the largest separation was due to Paul. He exhibited a function whose randomized query complexity is its quantum query complexity raised to the power of 8/3. On the other hand, Bansal et al. Showed that a quantum algorithm can have at most a quadratic speedup. Our work improves Toll's result by a polynomial factor. In particular, we exhibit a cubic separation between randomized and quantum query complexity using the cheat sheet framework introduced by Bansal et al. Our separation results in the query model imply similar results in the communication model. First, we show that there is a partial function whose quantum communication complexity is log n, but a randomized protocol would require at least n to the 1 minus epsilon bits of communication for an arbitrary small positive constant epsilon. This improves the prior work by a polynomial factor and is near optimal. This result follows by the lifting theorem, which transfers a harness result in the query model to the communication model. Analogously, we give a cubic separation of randomized and quantum communication complexity for total functions, which again improves prior works by a polynomial factor. At the heart of the analysis for all the above separation results is the following new Fourier analytic bound on decision trees, which we believe is important on its own right. In particular, we show that for any decision tree G of depth D, if we take the Fourier coefficients from the Fourier spectrum at level L, Take the sum of their absolute values. Then this quantity is bounded above by c to the L, where c is an absolute constant, times square root of d choose L times 1 plus log n to the L minus 1. This bound is essentially optimal. There are examples showing that the dependence on d choose L and on log n are tight. So this settles the conjecture by Hall. The previous bounds become trivial for a spectrum beyond the level of square root of d. And this is the main obstacle why the previous work didn't get the optimal separation. Independent of our work, Bansal and Sinha also obtained similar results, remarkably by a very different approach. Their approach uses the stochastic calculus, a more advanced machinery, where our analysis is Fourier analytical and more elementary in our opinion. A side product of our analysis is the optimal Fourier weight bound on decision trees, while their analysis did not attack this problem. Finally, our result is existential, while Bansal and Sinha's analysis works for an explicit function, i.e., the k-fold correlation problem. Now let me introduce you the problem Rorrelation. Here we have an orthogonal matrix U, a parameter, and we define the Rorrelation of k vectors as follows. Take the O1 row vector times the diagonal matrix whose diagonal is the vector x1 times U times the diagonal matrix of x2 times U times the diagonal matrix of xk times the O1 column vector. Then normalize this quantity by dividing n. This gives us a number whose absolute value is bounded by 1. Now we can define the Rorrelation problem, which is a promise problem. Its one instances are those inputs who have large Rorrelation, larger than 2 to the minus k. And the 0 instances correspond to those with small Rorrelation in absolute values, smaller or equal to 2 to the minus k minus 1. We don't care the other inputs. This definition already suggests a natural quantum query algorithm. Indeed, there is a quantum algorithm using k over 2 queries that accepts any input x with probability the Rorrelation of the inputs plus 1 divided by 2. A slight modification of this algorithm solves the Rorrelation problem with the right error parameter. So really the hard part of the analysis is to lower bound the randomized query complexity of the Rorrelation problem, for which we follow an indistinguishability argument. Here we have two distributions. One is a uniform distribution, the other is a carefully chosen correlated distribution. The uniform distribution has a concentration property, namely, a uniformly random input will have small Rorrelation with high probability. In other words, a uniformly random input will be a 0 instance with high probability for the Rorrelation problem. While the correlated distribution has the anti-concentration property. So a random input sampled from this distribution will be a 1 instance with high probability. Thus, if a randomized algorithm G solves the Rorrelation problem with a small error, then it should be able to distinguish these two distributions in the following sense. Evaluate G as the inputs sampled from the correlated distribution, the expectation should be close to 1. And evaluate G as inputs sampled from the uniform distribution, the expectation should be close to 0. So the two expectations have a large difference. However, we will show that the difference cannot be large if G is a shallow decision tree. First, apply the Fourier expansion to G and observe that if we take the expectation on the empty character, we always get 1. The constants from two terms cancel out. If we take the expectation on the non-empty character over the uniform distribution, we get 0. Therefore, this expression simplifies to a weighted sum. Sum of the expectation of the characters over the correlated distribution weighted by the corresponding Fourier coefficients. Now we group the terms based on the level of the Fourier spectrum, some from level 1 to level n. Within each level, we take the maximum value of the expectation of characters at that level, then multiply the L1 norm of the Fourier coefficients at that level. This second factor has been analyzed by Tall. He proved that this term decays exponentially fast with respect to L for a random orthogonal matrix. Plug in our Fourier weight bound, one can calculate that this entire summation is small if the decision tree is shallow. This concludes that the randomized query complexity of the Rorrelation problem has to be large. Next, we move on to the analysis of the Fourier weight of decision trees. In this part, we want to give an upper bound on the L1 norm of the Fourier coefficient at level L. We will use the shorthand notation for this big summation in the remainder of this talk, meaning level L Fourier weight of tree T. In particular, we will prove the following. For tree T, that can output -1 in addition to 0 and 1 of depth T. If the density of tree T is P, so the fraction of the inputs that have non-zero output is P, then the level L Fourier weight of such tree T is bounded about by C to the L times square root of D choose L times this lambda function on P, where the lambda function is a segmented function whose precise expression is the following. And we won't worry about it for this talk. But this lambda function has some nice properties. For example, it's increasing and concave. And if we plug D equals to 1 into this expression, we get the square root of log n to the L minus 1, which showed up in the previous slides. Now I'll give you a high-level idea of how we prove the Fourier weight bound of decision trees. Here we have a decision tree T and fix a leaf B. Write down TB, the label of the leaf, times the indicator function indicating whether an input would reach this leaf. Take the sum over all leaves, we get a function computed by tree T. Now we massage this indicator function a little bit. We write it as the sum of product, and we can move the summation to the front. Now the level L for a spectrum corresponds to the summation over all the subsets of layers of size L. This expression can be interpreted as follows. Select L layers and consider the contributions to the Fourier weight from the characters formed by the variables of the selected layers on each pass. Sum the contribution over all paths and all possible ways of choosing L layers recovers the level L Fourier spectrum of T. Next, we want to focus on the special family of subsets of L layers, which we refer to as the elementary family. In more detail, here we take I1, the consecutive layers of the tree, and then I2, I3 till IL. So these are consecutive but disjoint layers of our tree. And we sometimes call I1, I2, IL intervals. The elementary family with respect to these intervals is the set of all subsets of L layers that contains exactly one layer from each interval. And we further restrict the trees with respect to the elementary families. In particular, we study the contribution to the Fourier wave from the characters formed by taking one variable from each interval for all paths. Of course, there are many different ways to choose these intervals. And our idea is the following. We are going to find a set of elementary families such that the sum of trees restricted to these elementary families recovers the level L Fourier spectrum of T. Then we bound the level L Fourier wave of tree T by analyzing the contribution to the Fourier weight from each restriction. In our paper, we will prove the following two theorems. First, we prove that the contribution to the Fourier weight restricted to any elementary family is proportional to the square root of the size of this elementary family. In particular, the contribution for any restriction is bounded by C to the L times the square root of the size of the elementary family times the lambda function on the density of the tree. This reflects the bound on our main theorem. Second, we prove that all the subsets of L layers can be partitioned into elementary families in an efficient manner. In particular, we will be able to find a partition of elementary families such that the sum of the square root of their size is approximately the square root of the total number of the subsets of L layers. Put all pieces together, we get the claimed bound. Now let me make a quick comment. Theorem 2 is not true from what I said. In our paper, we need to define the elementary family in a more sophisticated way. Namely, we will allow picking up to 2 variables from one interval. I would like to end this talk with 2 natural open problems stated here. Thank you for your attention.